All right. Hello, hello, everyone. Happy Friday. So, yeah, exactly. We got a weekend. My favorite. And maybe some snow. We'll see. I don't have to shovel at my house, so I'm a fan of snow. Okay. So we're going to begin today by finishing up thinking about veins and dialing in a little bit on our understanding of how they can affect the heart, how they can affect blood pressure. So we're going to start off with a little kind of application question here. So last time we were talking a little bit about how we move blood through the veins back to the heart. Right, so one of the applications of this does have to do with ways we can deal with different types of diseases. So here we have an example of someone who has a disease called chronic venous insufficiency, and they're getting some swelling in their legs, particularly when they're standing. Even if you don't have this, you might have found that if you stand around for a long time, maybe your legs, maybe your feet start to swell. So their doctor is telling them that they should start doing some ankle flexion exercises. So moving their ankles around during the day. So with our understanding of Wednesday's content, what might we think is happening here? Why is this a good recommendation? Why is this something that could help with this swelling in the legs? Take a look at some of our guesses. Okay, cool. So a variety of choices here, but yeah. So this is pulling in those pumps that we were talking about last time. So how we get blood flow from the periphery to fight against gravity and come back to the heart and continue circulating around. So we talked about two pumps last time, the skeletal muscle pump and the respiratory pump. So we looked at how muscles can create a sort of limited pressure gradient that helps us pull blood from the veins back up as we squeeze muscles, activating those muscles, like in this case, by doing some ankle flexion exercises, exercising those muscles in the leg that you've seen in lab. So that would squeeze the leg veins, right, as those muscles contract, pushing blood up because we're creating then high pressure in the leg, lower pressure above the leg, moving in that upward direction because of this pressure gradient, and not falling back down to the feet because we have these valves allowing for unidirectional flow back towards the heart. So this is a way we can reduce swelling. That's what we were talking about last time. Part of the reason for the swelling could have something to do also with our pressures, our NFP, maybe altering filtration, but this is why this is kind of a fix. Okay. Cool. All right. So we're going to continue thinking about veins, vein pressure, and focus in on the idea of venous return. So returning this deoxygenated blood to the heart. So we can use the right side of the heart to pump it to the lungs, and then the left side of the heart to pump that newly oxygenated blood back to the body. Okay. So a reminder about venomotor tone. So we mentioned that smooth muscle in general has tone, right, before. So that kind of tension in smooth muscle, where we have this kind of intermediate tension where we can dilate and constrict from that base amount of tone, which is a little different than how a skeletal muscle works, right? So skeletal muscle, when it's relaxed, is just fully relaxed and then always shrinks when you contract it. Doesn't kind of go both ways with nervous activity. We're always activating or just stopping. But our smooth muscle, we can dial in either direction a little bit. So we have smooth muscle around the veins. So we do have tone around the veins. That's what our venomotor tone is. And we want to link this up to our idea of compliance. Okay, so we have got a little reminder figure that I popped in here from one of your previous slides. So just a reminder, when we think about compliance, we're thinking about a relationship between volume and pressure. Usually we think about arteries with their low compliance. So they're that lower line here, right? Smaller amounts of volume create higher amounts of pressure with that low compliance state. And in veins, which are highly compliant, our low volumes would create really low pressures, but even high volume doesn't create all that much pressure in a vein. However, if you change the smooth muscle around a vein, you're basically changing the tension in the wall, right? So you're changing how tense the wall of a vein is. Usually it's all big and baggy and floppy. That's that high compliance. So what we mean when we say increase in venomotor tone, so we're talking about a little more tension in the wall of the vein because we have a little bit of contraction of that smooth muscle. And this happens through activation of the sympathetic nervous system. So we talked before when we were talking about arterioles, most of the body has alpha adrenergic receptors. They respond to norepinephrine in particular, but also high concentrations of epinephrine. And what they do is they constrict smooth muscle when they're activated, right? So that's working the same here on venomotor tone, the same way it would on an arterial, right? So when we tense up those walls, we're changing the compliance here for our veins. We're making our veins a little less floppy, so they're going to become a little more like an artery. They're going to change their compliance, be a little lower in the compliance here. Okay. So when that happens, right, we think about our arteries as being under high pressure. Okay, so when we change the venomotor tone and therefore change the compliance, this has the effect of also changing the pressure in that vein. So now we have a slight rise in the pressure in the vein, and we particularly care about that when we're thinking about the central veins, so the ones leading right back to the heart, because the difference between those central veins and the right atrium during diastole are what influences how much blood is going to flow into the heart, how much that heart is going to fill. Okay. So we got tension around the veins, that's our venomotor tone. Sympathetic nervous system activates alpha receptors. We got a little constriction. That means we're now a little less compliant, we're a little less floppy, which means we've got higher pressures. Higher pressures can create a temporary pressure gradient to increase return to the heart. Okay. So the next several slides are walking through this in a kind of big picture flow, thinking about all the factors that affect our veins. There you go. Cool. So up at the top of this figure, which is from your textbook and you have in your slides, we're looking at the different things that we might think about related to our veins that ultimately are going to have effects on the heart and effects on our mean arterial pressure, which is essentially a weighted average blood pressure. So we'll step through it, but we're going to be thinking about how we have our muscle pump that we just spoke about, that skeletal muscle pushing blood affecting this. We have our respiratory pump. So when we change pressures in the thorax, we can essentially suck blood kind of up into a low pressure system like a vacuum. When we change nervous activity, we change our venomotor tone. So we also change the pressures in the veins, change our flow, and just pure amount of blood in a vein can make a difference. So blood volume is one of our stimuli here we're thinking about as well. Past this first block, right? Everything is going to work the same for all of those factors. Ultimately, in the direction that we're looking at, increasing mean arterial pressure, increasing blood pressure. So all of these things, if you upregulate them, make them more active, are going to increase blood pressure. So in this flow chart, we're just seeing here this sympathetic nervous activity dialed in. So we have that sympathetic nervous innervation to the smooth muscle surrounding the veins. The veins, their smooth muscle, has our alpha adrenergic receptors, right? Alpha adrenergic receptors, when we think about them kind of anywhere in our cardiovascular system, or at least in our vasculature, we want to think about constriction, right? So making that radius a little smaller, making it a little more tense. In veins, we're focusing on that tenseness, the venomotor tone. So the same thing is happening. We've just got kind of a new vocabulary term here. Okay? And that tenseness means that we're less compliant. So now if you put blood into that vein, right, it's not going to low pressure just kind of expand out. It's going to keep a little bit of that tone. So we're going to see a rise in pressure when we put blood into it. And so that's our drop in compliance. We don't need to think about the venomotor tone or the venous compliance for those other three factors. So the muscle pump, the respiratory pump, and increases in blood volume just kind of directly increase venous pressure, right? So the muscle pump by squeezing, the respiratory pump by changing pressures in the thorax, and blood volume by just changing how full that vein is. So all of these factors would increase the pressure in our veins. So you can see this little up arrow by our venous pressure here. Okay. So when we think about that venous return and that venous pressure, right, we're thinking about that relationship where we have our heart, we have our chambers, so ventricles down here on the bottom at the apex where we see this V shape. So we're going to have a right ventricle, a left ventricle, and a right atrium, and a left atrium, okay? And our veins are returning to this right atrium. So from below, you'll see in lab, when you look at the hearts, we've got an inferior vena cava. From above, we have our superior vena cava, but we're all leading into this right atrium. Okay, so that's our direction. Okay, so when we're thinking about why we care about this difference in venous pressure here, right, we know that flow is equivalent to a pressure difference divided by resistance, right? So if we change our pressure difference, if we increase a pressure difference, we're increasing flow. So we can think about this venous pressure change as creating higher pressure here. Right? And when the heart is relaxed, we should have low pressure in that atrium. Right? So we are going to, on the whole, have more blood filling into that right atrium when we're relaxed. So that's why we see this increase in what we refer to as venous return to the right atrium and also to the left atrium if we were focusing on the lungs. But we're really focused exclusively on the systemic circuit for most of this unit. Okay, so we're focusing on the right atrium here. All right. So that's what's happening during diastole. So during the relaxation phase, and particularly during that first part of the cardiac cycle we spoke about, when we're going from filling of the right atrium and then into filling of the ventricle, okay? So we can think about this next bit in terms of these pressure differences too. So I'm erasing this label of high and low because we're moving forward a little in time, right? So we've increased venous return to the right atrium by increasing that venous pressure and creating a gradient between the veins and the right atrium. But as we move forward, that means that we're filling the right atrium a little bit more, which means that we have an increase in the pressure in the right atrium as we start to move towards systole, towards this ventricular filling. Okay. So we're seeing an increase in atrial pressure as we have more blood moving in. Okay. So that sets us up for this next little piece, right? So this means increase in atrial pressure, means our preload for the heart is a little more. So we're also increasing the pressure that we see at the end of diastole, right? So essentially, we're going to be able to squeeze out more blood because we have more blood and we're creating this higher pressure in the heart as we're filling it. This is related to the end diastolic volume, right? So our greater pressure at the end of diastole is also reflective of a greater volume of blood in the heart at the end of that relaxed phase, at the end of that filling phase. So this means that we can squeeze out more blood. Our stroke volume goes up, right? So what we've just done, let's put on the pressures here, right? So we created more blood coming into the right atrium. So as it filled, it got to a higher pressure. You remember that blood in the heart moves down pressure gradients. So went from high to our empty-ish right ventricle, flowing down that gradient. That's still happening during diastole, right? So we split diastole a little bit in half when we looked at our cardiac cycle phases, right? Overall, we're getting more blood ultimately into that right ventricle here. We could measure it in terms of its pressure and its volume at the very end of diastole, right before we start to squeeze. And during systole, when we start to squeeze, we increase our stroke volume because partially we can think about it as there being more blood in there, but we also mentioned in ANP1 that the heart has an optimal muscle fiber length, and it's actually not at optimum when it's at its kind of smallest state. So we know that when we stretch it out a little more, when we fill it a little more, that even lets it contract more, and lets it contract harder. So overall, we've increased our stroke volume, okay, which means we are going to increase our cardiac output because cardiac output is our stroke volume, right? The stroke volume is the amount of blood per heartbeat times our heart rate, which is our beats per minute. So now our cardiac output is how much blood is moving into our systemic circuit per minute. So we've raised our cardiac output just through doing all this stuff to our veins, right? So just by changing how much blood we're returning to the heart, because we're moving our pumps a little more, our sympathetic nervous system is a little active more, changing the tone, changing the pressure in the veins, we've increased stroke volume and cardiac output. Okay. This is finally going to increase our mean arterial pressure as we put more blood into the aorta, right? So greater volume of blood into the aorta, greater cardiac output means we have a greater pressure because there's this relationship between pressure and volume, where more volume makes up more pressure on those walls. All right. So that was a lot of words. I did a lot of talking and scribbling. Questions about this process here? I want you to notice sometimes, at least I think some of the difficult part to remember, sometimes in this unit can be the actions of the different parts of the nervous system. But conveniently, when we're thinking about the vasculature, that sympathetic nervous system is really acting in conjunction, like its effects on the blood vessels are similar to its effects on the heart, right? So we know that the sympathetic nervous system also increased heart rate when we talked about the heart, right? So increased heart rate, it had innervation to the ventricles themselves, so it increased contraction and stroke volume all on its own. Now we're just adding on that it's also touching your veins. And when it touches your veins and increases tone, this is another way it's got to flow all the way down, increasing our cardiac output and increasing our blood pressure, which we like because when the sympathetic nervous system is active, this is our fight or flight part of the autonomic nervous system. You want to keep blood pressure up because you need blood going to your muscles, you need blood going to your heart, you need blood going to your lungs because you're going to go do stuff. You want to keep lots and lots of oxygen going to all these tissues so that you can produce lots of energy and use that energy to actually get out of a stressful situation. That can be a lot to remember, but some of the stuff you can kind of work backwards. Okay. So stepping back to the sort of list of facts we would want to remember. Let's check off all of these things that would ultimately increase how much blood is returning to the heart, so our venous return, and therefore ultimately increase how much blood is coming out of the heart, so increasing our cardiac output. You can't select multiple? Oh, all right. Yeah, in that case, go ahead and select the one that's false because there is actually only one. The ones that turn green will be wrong in a second, but we'll talk through it. I won't judge any of you if this graph that we're about to see looks janky. So maybe choose in your mind and we'll take a look there. Okay. Since it's messed up, let's look at the answers. Okay, cool. Yeah, so the one that was wrong here was the compliance piece. So anytime we have an increase in, weird that it let me put multiple answers. Anytime we see an increase in sympathetic activity, that's going to increase the venous return and cardiac output, as we just walked through. Anytime we increase our activity of the muscle pump, we're returning more blood to the heart, increasing venous return and cardiac output. Same thing with the respiratory pump. Same thing would happen if we increase just purely how much blood is in the veins. Okay, so the one that's wrong is the increased venous compliance. That's because when we're looking at that compliance relationship, right, we've got volume here, we've got pressure here. And to help us remember what high and low mean, we're going to remember that our arteries are low and our veins are high. Right? Okay, so what's happening here? Right? We're thinking about pressures. We know that we want higher pressure in the veins in order to increase venous return. Right? But if we looked at a fake line where we had higher venous compliance, right, this would mean that if we're reading our relationship between the amount of volume and the amount of pressure, a little dotted line, right, a more highly compliant vessel would have super low pressure, right, versus a more lower compliance here, right? We have increased the amount of pressure, even if we don't change the amount of blood in the vein. Okay. So I always find it a little helpful to think about this graph and this picture first when you're reading statements about compliance. Okay. Cool. We're now going to move on to lymphatic system for about 2 slides, and then think about mean arterial pressure. Okay. So our notes on the lymphatic system, right? The lymphatic system has a number of functions. So one of the pieces that is probably most familiar to us in daily life is actually the last bullet point on this slide. We're not going to talk about it at length right now, but it is part of the immune system. Your macrophages are there. We've got various types of immune cells there. It's acting to kind of filter out pathogens. And to do that, in part, it has to be related to flow of fluid through the body, like through your whole body. Okay. So it has its own system that basically kind of looks just like veins, except for we have some swollen bits, we have some lymph nodes. Okay. So we've got lots of vessels that look kind of vein-like. We've got some nodes. There are some lymphatic organs related to this system as well. Okay. And for our purposes right now, as we're thinking about fluids and the amount of blood we have in the body and how it's moving around the body in the cardiovascular system, what we want to know is that our lymphatic vessels are responsible for all that extra fluid that we filtered into the tissue when we were doing our net filtration pressure stuff. Right? We said it's about 3 liters extra per day is ending up in tissue versus in the veins. Right? So some of the fluid that we filter out at the start of a capillary will come back and be reabsorbed at the venule end, but a lot of it wasn't, right? That force for absorption, even at the venous end, was kind of low. Okay. So we have all this fluid buildup around the capillaries in the tissue, and our lymphatic system is going to kind of come back and sweep and move that fluid ultimately back into your cardiovascular system, because you don't want to just have drops and drops and drops in blood volume throughout the day. So it has a relationship to the capillaries. It's not directly connected to them like end to end, like our arterioles to capillaries to venules are, okay? But it's right next to them. Okay. So some of that fluid that came out of the capillaries and didn't return into the veins is going to move into our lymphatic system, become part of our lymph. And ultimately, lymphatic veins dump back into our normal veins. So you'll see in lab eventually a structure called the thoracic duct. That's like a big lymphatic vein. Big, we mean big for lymph. You'll see it, it's kind of tiny when you see it with the naked eye, but it's coming back to the veins and going into the right atrium. So right there, kind of at the heart. So lymph moves through the lymphatic veins just like it does through our other veins, using these various pumps, using some little valves as well. The other time we'll see lymph come back way in the future, but lymph does have a little bit to do with absorption of fats and stuff from your GI system. So it'll get mentioned again, but not for a little while. So here's what it looks like. If you wanted to see the lymphatic system, the traditional color on figures for the lymphatic system is green. In person, it doesn't really look green, but it's a helpful contrast to our red oxygenated blood, mostly moving through arteries, and our blue deoxygenated blood, mostly moving through veins. So we can see all those pieces that we've been talking about thus far, right? So we have our blood flowing out through our aorta, through our arteries, through our arterioles, into our capillary beds, where we can sort of shift blood into the capillaries through actions of constricting meta-arterioles and loosening precapillary sphincters, or we can do the opposite, right? Forcing blood into the capillaries versus letting blood kind of bypass through capillaries. But we know that on the whole, we've got fluid moving into this area next to the capillaries, right? And that's where we would pick up with our networks from the lymphatic system. So these would be little lymphatic capillaries, we could call them. Here, this network, this bed, right, moving into vessels that look similar to the rest of the vasculature. We're going to hit some lymph nodes where we have some filtering going on, where we have some immune function kind of concentrated. And we're going to continue flowing back towards the heart. And like in the veins, we've got some valves to make sure that this flow is still unidirectional. So you can see here the connection to the veins happening here right before we head into the right atrium and head into the heart. So we've now got that fluid back, so we don't have dropping blood volume over the course of the day. That's kind of what we want to know about the lymphatic system for now. They work kind of like veins. They're helping us return fluid towards the heart, and they're kind of cleaning up, picking up that fluid that we left around the capillaries due to high filtration happening when we calculate our net filtration pressure for our capillaries. So we're now going to move to starting to talk about our mean arterial pressure again. We're going to be thinking about regulation of blood pressure. But to do this, we're going to be thinking a bunch again about the nervous system. And so we want to think a little bit about how the nervous system, again, is related to our cardiovascular system. So you're going to imagine that you're going on spring break to Florida, you're walking around, you see an alligator, freak out and run away. Okay. So this is going to have an effect on your cardiovascular system due to a couple of different reasons. So I want you to jot down a couple of things you know about the situation. So some things that might be happening here that might be related to what's going on in our blood vessels and in the heart before we talk about this next bit, how we're affecting our mean arterial pressure as we sum this all together. I'll give you a couple minutes to do that. All right. So let's refresh our memories a little bit. So good job. I love hearing chatter. We're going to dial it in for a sec. So your list of things that you thought of might be a little different than my list, but some things that I hope we can kind of piece together here. All right. So hopefully we could identify here that what we're doing is activating the sympathetic nervous system. All right. So from ANP1, we know that our sympathetic nervous system, when it's activated, is going to get our heart rate up, affecting cardiac output, increasing it. It's going to get our stroke volume up by increasing our ventricular contraction. All right, so cardiac output going up there because we have that communication with both the electroconduction system of the heart as well as the myocardium of the ventricles itself. Yeah. And from this unit that we've been talking about the vasculature, right, we can think about some local effects on the vasculature separate from the sympathetic nervous system. Right? We've also talked about the sympathetic nervous system's effects on smooth muscle, but thinking about local effects that we might have kind of set back in our memory a while ago, right? When we're going on this run, running away, we're activating our skeletal muscle, our tissue is moving, we're using muscle, which means we're burning energy, which means we're depleting oxygen as we do our cellular respiration, using oxygen to burn up glucose, basically. Okay. So we're going to see that we need increased blood flow to the skeletal muscle. So one of the immediate ways we do this is through just local effects. When we see those low oxygen concentrations in the tissue next to our, or sorry, in the fluid next to our tissue, so right between our muscle and the arterial and capillary bed going to it, we're going to see low oxygen here. We're going to see high carbon dioxide as we are doing lots of metabolism. Carbon dioxide is our waste product, basically. So we're going to use our active hyperemia to increase blood flow here so that we can get more O2 and sweep that carbon dioxide away, because carbon dioxide buildup is not good for your body. So from the extrinsic effects is where we'd be coming back to that sympathetic nervous system. So we know that our neurotransmitter for the sympathetic nervous system is norepinephrine through most of our roots. And we've got a relationship to the adrenal glands. So from the adrenal medulla, we've got our epinephrine as well. But we know that the norepinephrine in particular is binding to alpha receptors throughout the body. Right? So where we have those alpha receptors in smooth muscle, norepinephrine preferentially binds to it. When that happens, we get vasoconstriction. So that's going to be true for our arterioles, as well as smooth muscle surrounding the veins, creating that change to venomotor tone that we just talked about. So when we have this change to our arterioles, we talked about that relationship with total peripheral resistance. Right? So when we clamp down on an arteriole, right, we're making its radius smaller. So we are increasing our resistance, and we have a relationship between resistance and flow and mean arterial pressure. So this is also increasing mean arterial pressure through the effect on the arterioles. We don't want to forget about the epinephrine part. So the epinephrine part, coming from that center of the adrenal gland, is binding first to our beta-2 receptors. Beta-2 receptors are the ones that really prefer epinephrine, right? So at low levels, we're immediately binding to some beta-2 receptors. Those beta-2 receptors are in the heart muscle, so cardiac muscle, and the skeletal muscle that you're using to run, right? When we bind to a beta-2 receptor, that creates dilation, vasodilation. So we're increasing the amount of blood that's going to heart muscle and that's going to skeletal muscle at the same time as using norepinephrine to keep our blood pressure up. As that epinephrine gets higher, right, we're going to have some spillover when it's at really high concentrations. It could also bind to an alpha receptor, right? alpha receptors don't care quite as much as the beta-2 receptors do about which neurohormone they're binding to. Okay? So when we have high epinephrine, we also bind to some of those alpha receptors, causing vasoconstriction. Overall, our effect is raising that mean arterial pressure or raising TPR. And we know that this vasoconstriction is also increasing our venous return because we're dropping the compliance of our veins because we've increased the venomotor tone. And ultimately, this means the heart is pumping out more blood. And so our blood pressure goes up, that map goes up. Okay. So there are many things all kind of working together on the heart and on the vasculature as we activate the sympathetic nervous system and also use some of this local regulation stuff. Okay. So when we think about mean arterial pressure and how we regulate it, we're going to be thinking about those effects, but also we're going to be thinking about how nervous control and hormonal control kind of work together. Okay. So a reminder of how we kind of shift our equations around to focus in on mean arterial pressure. So our big relationship for this unit is that flow through any tube, like anywhere in the world, is due to a pressure difference divided by a resistance. Okay. And for our physiology purposes, when we're talking about flow, that means cardiac output. Our pressure difference that we're interested in, if we're thinking about cardiac output, is the difference between the mean arterial pressure and the central venous pressure. Central venous pressure is usually quite low, so we can abbreviate that pressure difference, wave our hands a little, and say it's essentially the same as our mean arterial pressure. We're going to divide it by a resistance, which is all the resistance in all the blood vessels throughout your body added up, mostly coming from arterioles, but not entirely. That's our total peripheral resistance, TPR. Okay. If we want to continue this, right, we also know that cardiac output is stroke volume by heart rate. Okay. So we're continuing reshaping this equation. We're trying to solve for mean arterial pressure. Right, so this is how far we get when we put in our equation for cardiac output. And then we can pull that TPR across to get our total equation for mean arterial pressure, which is going to be our resistance times our flow, which is our stroke volume, and our heart rate. Okay. So if what we're focusing on is mean arterial pressure, right, and what changes we see to it, how we might change it, how we might regulate it, right, we're going to be thinking about things that can affect these three factors. Right? And those are actually the only three factors we have to think about, right? Everything else we talk about that has an effect on mean arterial pressure has to somehow be linked to either our resistance, our stroke volume, or our heart rate. Anytime we increase those factors, or any one of those factors, we see an increase in mean arterial pressure. And anytime we drop them down, we drop down our mean arterial pressure. So we can do that with nerves, we can do that with hormones, and we are going to need to be able to sense what our mean arterial pressure is, because your body wants to regulate mean arterial pressure. You want to have a good blood pressure. You want to keep that consistent, because that blood pressure is what's maintaining appropriate amount of blood flow to your heart, to your muscles, to your liver, to your GI tract, to your brain, right? And that blood has oxygen in it. It's got glucose in it. So we need that stuff. Okay. So we're going to think about baroreceptors, low pressure baroreceptors, as volume receptors in particular. We'll also see that we have some stretch receptors involved in some of our reactions as well. Okay. So a reminder, what we're thinking about when we're thinking about mean arterial pressure in kind of physical terms, right? We're thinking about the flow of blood into the aorta, and then the flow out from the aorta, and we want to kind of keep the pressure going so that we have even flow to our organ systems, regardless of whether our heart is currently squeezing in systole or relaxing in diastole. When we see increases to mean arterial pressure, for example, if we increase cardiac output, an increase in mean arterial pressure would kind of look like a more stretched out aorta. We have that elasticity in the walls that's going to allow the aorta to bounce back. But when we put a bunch of volume in, we do see more stretch initially, right? So we see increases in pressure, increasing how much we stretch. If we allow it to flow around, we would get more flow out to the blood, but we're kind of limited based on this cardiac output. So if we leave total peripheral resistance the same, we're just going to see that pressure kind of building up here in the aorta. So now, when we have a cardiac output that stays constant, and we have increase of mean arterial pressure here in our aorta, we would see even more increase in mean arterial pressure as we increase total peripheral resistance and like block that flow. Okay. We'll talk through all of this further. Okay. So when we're determining our mean arterial pressure, we just reshaped that equation, but I'm going to write it up at the top here because this is really what we're thinking about. All right, our stroke volume, our heart rate, and I guess I put it over here before, so I'll put it over here again, our total peripheral resistance. All right, so all of that together is our mean arterial pressure. Okay. So when we think about stuff that controls it, one of the first things we're going to be thinking about is control of arterioles affecting TPR. Okay. And we've talked about a number of things that affect stroke volume and heart rate, but we're going to be thinking about overall right now, we're going to just think about stuff that affects cardiac output. Okay. So that might be veins, as we just talked about, might be sympathetic nervous system acting directly on the heart. We got to kind of add all these effects together. Fortunately, you're pretty much never going to see cardiac output moving in one way, but TPR moving the other way. If you have an up arrow, it's going to be on all of these factors, or just one of them, but you're never really going to have opposite directions. Okay, so we'll leave that there for now and pick up with how we're controlling this mean arterial pressure on Monday.